This lecture is about computational graphs, which are a way of visualizing the data flow and sequence of computations in any program, but are most often used for understanding forward and backward propagation in neural networks. Here we have a small slice of a neural network where we're showing one node in each of the last 3 layers and some of the edges coming into and out of those nodes. This visualization captures all of the computations going on in a neural network if we understand all of the implicit operations, like multiplying weights by activations, summing the incoming weights to a node, computing the activation function for a node, and computing the loss at the end of the network. But sometimes it's useful to make those different computational steps more explicit. Here I've drawn a slice from a computational graph where the goal is to make all of the implicit operations in the neural network representation explicit. So for example, in the computational graph we have nodes for the activation A1 and the weight W1, and those variables in the program are brought together into a node that computes their product. And then the product A1 times W1 is one of many inputs to the sum of all of the incoming values here. So this node computes the sum of weighted inputs for node 2. And so the output of this sum node is what we have been calling x2, the input to this node. And then that goes into a node that computes a sigmoid activation function, where the output of the sigmoid is A2. And then we proceed further, right? This output goes to several other nodes in the computational graph because several nodes at the next layer all receive A2 as inputs. But in particular, among those is that it gets multiplied with W2 and then summed with all of the inputs to node 3, which gives us the input x3. And then we compute a softmax, where that softmax depends not just on x3, but on several other weighted sums of inputs, all the others for this layer. And so that gives us the activation of this node, and then that activation is one of many inputs to a categorical cross-entropy loss that we're computing in order to start our backpropagation. So the idea of this computational graph is that everything that could be a variable in the program that implements this computation is a node, and we have edges in this graph indicating all of the dependencies between variables in the program. If our variable for this activation is an input to several other computations in the program, then it has edges to those other computations. And sometimes we're explicitly representing things that wouldn't be given a name in our code, but would be an intermediate value that is computed as part of a larger computation. And we could in fact break down some of these computations even further. We know that a sigmoid activation function is 1 over 1 plus e to the minus x. We could break that down into e to the minus x, 1 over 1 plus that intermediate result, or other levels of granularity. But the key choice in the level of granularity that we're interested in is that we want to know how to take the derivative of any node in our computational graph. Because our goal here is to represent both the forward and back propagation steps of our neural network. And so if we know how to take the derivative of any node in our graph, then it's clear how the partial derivatives propagate backward through the network. We could, in principle, use this computational graph to compute the outputs of a neural network. We would begin with a topological sort of the graph, where all variables appear after everything else they depend on. And so then we could go through the graph in order, and when we get to any given variable in the graph, we know all of its inputs, and so we can compute the value of that variable. But the real value of this representation is in showing where the partial derivatives of the parameters that we're modifying with gradient descent come from. When we do gradient descent on a neural network, the thing that we need to compute is the partial derivative of the loss with respect to each of the weights. So for example, the partial derivative of L with respect to weight 2. And by choosing the nodes of this graph such that we know how to take the derivative of any given node, we can use this graph to work our way backwards and figure out the partial derivative for any of the parameters that we want as part of our gradient descent step. For example, suppose that we have the output delta for this softmax node. That would be the partial derivative of the loss with respect to x3. So this would be delta for output node 3. If our goal is to carry the partial derivatives backwards through the network, then at each step we are applying the chain rule, where we are multiplying the derivative of this operation by our derivative so far. So if we have carried a derivative this far, then we need to multiply that by the derivative of this operation with respect to the particular input we're interested in. So here, if we take the partial derivative of a sum with respect to one of the inputs of that sum, all of the other terms in the sum are constant, and this one is linear, and so all of the others go to 0, and this particular term goes to 1. So the derivative of this sum with respect to one of its inputs is 1, and so through this sum, we just get 1 times the derivative so far, which just carries back that same delta. For a multiplication operation, we know that if we have two values, a times w, then the derivative with respect to a is w, and the derivative with respect to w is a. And so when we apply the chain rule, we will take the derivative so far and multiply it with the derivative of this node. So this is the partial derivative of the loss with respect to this operation star. So here we would get a partial derivative, which is this partial derivative times a2. So here we would get a2 times partial L over partial star, and that gives us the partial derivative of L with respect to W2. And if we carry our derivatives back this way, we get W2 times partial L partial output of this node, and that lets us carry the derivative back further through the network. When we get to a node that has multiple outputs, the derivative of the eventual loss with respect to this node is a sum over all of the things that it feeds into. So here we get a sum over all of these derivatives that we're carrying back for each of the nodes that it feeds into. So here we get a sum over all of these multiplications in the next layer of the derivative that we're carrying back here. Once we have that sum, that gives us the partial derivative of the loss with respect to this node's output A2. And so we can carry that back through this node by multiplying it with the derivative of the sigmoid function, which we know is activation times 1 minus activation. So that gives us a times 1 minus a times the sum of the incoming derivatives. And unsurprisingly, this is exactly the same partial derivative that we've derived before. It's just a different way of thinking about how do these derivatives propagate back through the network. So for any node, to carry the derivative of the loss back through that node, we're applying the chain rule, which means we're multiplying the derivative of the loss with respect to that node's output times the derivative at that node. So we could use this computational graph to compute all of the partial derivatives in the network by working backwards through our topological sort and propagating the partial derivative through each of the nodes by multiplying when we go through a node by the derivative of that node. And whenever we have a node with multiple outputs, we'll need to sum the derivatives coming from each of those outputs. Since this graph that I've drawn is just a small slice out of a much larger computational graph representing all of the computations going on in an entire neural network, it may not be clear how a computational graph works in general. So let's take a look at a much smaller example so that we're clear on what it means to calculate the result of a function or the derivatives of a function using a computational graph. So here's a computational graph where we are computing some function f of x, y, and z. What is the function that we're computing here? Well, we're adding together an exponential and a sum. So we will have y plus z plus an exponential. This is y plus z plus e to the, well, this is the sum of y plus z and x times y. So e to the x, y plus z. So what we've done by drawing this computational graph is broken this function down into lots of intermediate values that help us in doing this computation. And so we could give names to all of those intermediate values. If we wanted to compute the output of this function for some particular combination of x, y, and z, so let's say we had -1, 1, 2, then for this point in xyz space, we can compute the value of f by propagating values forward through the network. So x times y gives us -1. Y plus z gives us 3. The sum of a and b gives us 2. The exponent here gives us e squared. And then this sum gives us e squared plus 3. And so the value of function f at -1, 1, 2 is e squared plus 3. But we can also use this computational graph to give us the partial derivative of f with respect to any of our inputs, or with respect to any of the intermediate variables within the network. To pass derivatives back through the network, we need to know how to take the derivative of any node's function with respect to each of its inputs. So here, f is equal to b plus d. And so the partial derivative of f with respect to b is, well, d goes to 0 and b goes to 1. So partial f over partial b equals 1, and the same for d. The more interesting cases are nodes like the exponential or the product. So the derivative of node d with respect to its input c is, well, the derivative of e to the x is e to the x. So since this node is computing e to the c, this is e to the c for whatever value of c we had when we propagated the values forward through the network. For node A, the derivative of x times y with respect to x is y, and the derivative with respect to y is x. And for each of these, some nodes will again get a partial derivative of 1 for each of the inputs. So if we know how to compute the derivative of any of the nodes in our computational graph, then we can use those to run a backwards pass through the network and calculate all of the partial derivatives. So the partial derivative of f with respect to d we know to be 1. So we'll get a 1 here. Similarly here. Now as we work our way backwards, the partial derivative of f with respect to c is this partial derivative times the derivative of d with respect to c. So d with respect to c is e to the c, and on our forward pass we computed that c was 2, so we get 1 times e to the 2, and so this partial derivative is e squared. That's the partial derivative of f with respect to c. Then we continue. The partial derivative of a sum is 1, so we get 1 times e squared, so just e squared here, e squared here. When we get to node B and we want to get the partial derivatives for each of these incoming edges, we need to first sum up all of B's eventual contributions. So we have a contribution of 1 here, plus a contribution of e squared here, and so we get 1 plus e squared. So we get a total of 1 plus e squared as this node's contribution to the derivative of f. And so now, when we carry that back through the sum, well, the sum just gives us 1 as its derivative, so we get 1 times this on each of these edges. So we get 1 plus e squared, 1 plus e squared. For node A, we have e squared here, and we know that the partial derivative of a with respect to x is y, and with respect to y is x. So we will, using the chain rule, multiply the downstream derivative by the derivative of this with respect to each of its inputs. So here we get y times e squared, and here we get x times e squared. And so we know the values of x and y from our forward pass. So here y was 1, and so this becomes just e squared, and x was minus 1, so this becomes minus e squared. And so then finally for x and z, we now know the derivative of f with respect to each of them. For y, we need to sum over each of these edges, and we get 1 plus e squared minus e squared, so this just gives us a derivative of 1. Note that what we've done here is not to compute the full symbolic derivative of f with respect to each of its variables. We've instead evaluated the derivative at the specific point -1, 1, 2. Feel free to check symbolically that the partial derivative of f with respect to x evaluated at the point -1, 1, 2 would give you e squared. But since our goal in backpropagation is just to figure out which direction is the gradient pointing for our current inputs, we don't actually need the full symbolic derivative. We just need the partial derivatives for the weights that we want to change evaluated at the current data points. But where computational graphs really become valuable is if we think not just in terms of scalar variables, but in terms of variables, nodes in the computational graph, that correspond to vectors, matrices, or even tensors. Let's redraw the computational graph for a densely connected neural network, but instead of having a node for every variable, every activation, and every weight, let's instead have variables that correspond to vectors of activations or matrices of weights. To that end, let's name the vector of activations at this entire layer of the network A1 with a vector hat, A2 with a vector hat, A3 with a vector hat for our 3 layers that we're illustrating here. And similarly, we could call the inputs to each of these layers, x1, x2, and x3 with a vector hat, where these give the vector of all of the weighted inputs to this layer. And similarly, as we've done before, we could represent all of the weights between two layers with a weight matrix, which we'll call W1 or W2. So now if we draw our computational graph, we can represent the computation of a layer with just a couple of nodes. So now we have nodes in our graph for our vector of activations and our matrix of weights, and we can represent the weighted sum of inputs to this layer. So this is computing the vector x2 as the matrix vector product W1A1. And then this vector of inputs to the layer goes into our element-wise activation function, where we're applying the sigmoid element-wise to our input vector, and this gives us the vector of activations A2. Then similarly for the next layer, we can get its vector of inputs by a matrix vector product. So this gives us our vector of inputs to the third layer, and this vector of inputs to the layer goes into a softmax activation function. And now, rather than having to think of a separate softmax activation function for each of the different outputs, where all of those softmaxes have to take all of the x inputs, we now give this input vector to a single node that computes the vector of softmax activations. And finally, we can think of this softmax activation as being an input to the loss function, where we are computing the categorical cross entropy, and the other input to this categorical cross entropy function is our target vector of what we wanted the output of the network to be. And so now we can think of our vectorized neural network computations as a computational graph that operates on matrix and vector variables. And the advantage of this computational graph representation is that we've broken out the steps of the computation to show that for each layer, we are first computing the weighted sum of inputs, and then we are applying the activation function. And we know how to take the derivative of the activation function, and we also know how to take the vector derivative of this matrix vector multiplication. If we want to use this computational graph to compute the gradient of the loss with respect to the network's weights, then to pass the derivatives backwards through the network, we need to apply the chain rule at every step, and we need to know how to take the derivative of each of these intermediate variables with respect to their inputs. If we think about the same example from before, where we have the deltas for the output layer nodes, and we want to propagate those backwards to give us the deltas earlier in the network, the output layer deltas correspond to the partial derivative of the loss with respect to x3. So as we are propagating backwards through the network, we have minus the deltas for this third layer. So the partial derivative of the loss with respect to the softmax inputs corresponds to this output layer delta. And so now if we want to propagate that backwards through the network, then we need to know the derivative of this matrix vector multiplication. But from multivariable calculus, we know that if we have a matrix vector multiplication, if we're multiplying matrix M times vector V, then the derivative of this with respect to m, so the dm of this thing is v transpose, and dv of this thing is m. So if we apply the chain rule, then we will get the incoming derivative times the derivative of this node. And so for the weights, the derivative is the activation vector, and so we'll get the deltas for the next layer times the transpose of our activations. And for this one, we will get a derivative which is the weight matrix. So we'll get W2 times our next layer derivative, which is the delta 3 vector. And I'm probably off by a transpose on one or both of these, but if we get the shapes to line up, then this corresponds exactly to the one that we computed by hand when we worked an element at a time up here. So we could have done all of the derivations that we did previously, where we thought about the partial derivative of one weight at a time or one input at a time, if we had worked in terms of matrix and vector calculus. We could have just started from this computational graph representation and talked about passing the derivatives with respect to these matrices and vectors back through the computational graph. But this alternate derivation allows us to zoom out and think about the computation of an entire layer at a time, and this will make it much easier to derive the operations that we want for more complicated layer structures like convolutions.